Hmm. Hmm.
One much smaller. Let me give you one. Let's do this. Remember? Like, give me a CBO. Right.
Hmm.
Nothing of that.
Okay. I don't know where the TAs are. Okay. Well, they'll catch up. So we're starting a new section, spectroscopy. Who likes physics?
Why would you say that?
Why do why would you say that? Because we're gonna talk about light.
This whole place, no.
Okay. Well, we have to review some of the light theory. You probably taken that at some point in high school. I don't know why Siri is objecting to physics, I guess. Yeah. All right. Let's see where we're at with what you know about light. The following are associated with a light wave. What? Which? C. Okay. What else do you have? It is all of them. So that the light has two characteristics, like two types of characteristics. Wave-like characteristics and pockets of energy, which is known as photons characteristics. So all of them. So following spectroscopy as means of analysis, detection can be based on absorption of a photon of light, emission of a photon, or dissipation of heat. What do you know for sure is correct? Can absorption of light. We did the caffeine lab and you were measuring absorption at 280 in the UV. But what about emission? Don't we do fluorescence? Yeah. Fluorescence is the measurement of emission of light. Okay. So we can do absorption of light, we can do emission of light as means of detection. What about dissipation of heat? So let's try to remember something. When do you remember ground state and excited state? Okay, so do you know when a atom or a molecule gets to an excited state, it has to go back to ground state. It can't stay at excited state. Is there dissipation of heat when it goes down from excited state to ground? Yeah, there is a little bit of dissipation of heat. Some molecules and atoms actually emit energy in a form of light and also dissipate some heat, but the dissipation of heat is very, very, very small, cannot be measured, so it's not used as a way for detection and quantification. So only A and B. All right, so this kind of summarizes what spectroscopy is about. So in spectroscopy, we have two types of species that can interact with light. So molecules and atoms. Some of you had done atomic absorption already in the lab. So that is an interaction of atoms with light. So we have the interaction of the matter, whether it is atom or molecule, with the radiation. We have different types of interaction. We have the absorption, either you absorb light or absorb and emit. In order for emission to happen, we have to absorb light first. So absorption, and then absorption and emission, or light scattering, diffraction and refraction. We'll talk about diffraction and refraction, how that happens and why is it relevant to us. And then there is the electromagnetic region, which means basically is categorized by the wavelength, and we'll define what wavelength means in a little bit. But there are different types of energies, and it ranges from radio all the way to gamma rays. The shorter the wavelength, the higher is the energy. So, and I will demonstrate that in a little bit. But the region that is in blue, green, and red is the region where food analysis it's relevant to food analysis. So absorption and emission happens in near UV and visible. Absorption also happens in the infrared, but there's no emission in infrared. Okay. Good so far. All right. So basically here is just showing you the different categories of spectroscopy. We have the UV vis absorption. We have the atomic absorption. Some of you did the lab already, where it is mostly for element detection or mineral detection when it comes to food analysis. We have infrared IR. So we have mid IR and near IR. We have a whole lecture on that. And then we have fluorescence. We'll talk about fluorescence and application of fluorescence. So it is also in the UV vis range. So UV vis absorption or UV vis fluorescence. ICP, inductively coupled plasma emission spectroscopy. There will be an abbreviation for it later. You don't have to remember it now. It's also for mostly element detection in food analysis. There is NMR. There is a chapter in your textbook, but I'm not going to cover it in this class. NMR, usually you need a semester or more to learn about NMR. And then mass spectrometry is not really a spectroscopy. It is in the section of the book under spectroscopy, but there is no interaction of light. You have spectra. You see spectra as a data that you get. And also with spectroscopy, you get a spectra in the form of data, but it is not, has nothing to do with interaction of light. It's a separate way of detection, and that was already covered. Okay, so applications. Where do we utilize spectroscopy in analysis? Identification. Okay. Identification of unknowns that we know that they could interact with light, either absorb or emit light. What else other than identification? What did you do in the caffeine lab? Quantification. What were you going to say? Quantification. And what about you? All of you wanted to say quantification. Very good. All of you get your points. All right. What else? Let me show you. So quantification, identification, there is qualitative detection. So detect, identify, and quantitate. So these are three different things. So detect the presence of something, try to identify what it is, and then sometimes you quantitate. In spectroscopy, we try to do structural elucidation, meaning trying to determine not only the molecular weight, but or formula, but also try to look at the structure. In IR, for example, when we cover IR, we're going to look at how we use IR to determine functional groups within a big molecule or a compound. NMR is big on structural elucidation as well. Compositional analysis, this is kind of part of quantification. We can do compositional analysis usually using mid-IR or near IR. When we calibrate these instruments, we can do quick determination of total moisture, ash, protein, fat. So we'll talk about that when we cover IR. Quality assurance and forensics. A lot of time, let's say we want to know if we have melamine in a particular pet food. So we know the spectra of melamine. We can run diagnostics and determine whether or not we have that particular contaminant. Okay, we'll give more examples as we go, and also the entirety of a lot of the coming chapters will talk about use of spectroscopy for identification, for detection, identification, and quantification. All right, so we'll do some definitions. Here's where we go back to the P word, which is physics. Sorry, well, what's that? I'm sorry, but it is what it is. Okay, so we have, like I said, we have wave-like properties and energy pockets properties or photon properties for light. So when we talk about the light wave, we have electric field and we have magnetic field, and they are a sequence of oscillation. So then get where is them here? Oscillation. So it is the repetition of similar occurrence. So here we have an increase and a decrease, another oscillation, another oscillation. So the distance between the maxima within one oscillation and the next is your lambda or wavelength. Okay, so this distance, and then here on the x-axis of the E, the height is the amplitude. So what you really want to know here, you want to know what wavelength is. So the distance between two maxima. And what you also want to know is the frequency. How many oscillation there is in a unit space and time. So the frequency is the number of occurrences of a repeated event per time. So number of oscillations per time. So the more oscillations you have within a specific period of time, the higher is the energy. The more oscillations within one specific period of time, the higher is the energy. And that relates to what we said earlier, the smaller the wavelengths, the higher the energy. Because with narrower distance between two maxima, that means you have more oscillations within a unit time. So the smaller the wavelengths, the higher the energy. So if we go back to this over here, so radio is the longest wavelength, all the way to gamma, the smallest wavelength, and then from here upward, the energy increases. So you have more oscillations, more energy within a unit time. Is it all coming back to you? The physics? Physics of light? Okay, So there are a couple of characteristics when we talk about wave-like properties. There is something we call interference. This is really important when we talk about the later on IR instruments and how light is projected within an IR instrument. Sometimes we project the light in a way that the waves cause amplification. So, meaning they meet in space where the maxima are coinciding with each other and the minima are coinciding with each other. So there is an amplification of the wavelength. Sometimes we do that in IR instrumentation to enhance sensitivity. Sometimes also we do cancellation so that to reduce interference from other compounds that might absorb in a specific region where you don't want it there because it will interfere with what you're trying to identify and detect. So in this case, we try to have the wavelength meet in space where the maxima is meeting with the minimum, so they cancel each other. Maximum here and minimum here, they cancel each other. So one is the one on the top, amplification to enhance sensitivity. The one at the bottom to remove interferences. So in instrumentation, when I talk about IR, they use mirrors to kind of direct the wavelength in a way to either amplify the signal or cancel a specific signal. So diffraction is very important in quantification when to apply Beer's law. Do you remember Beer's law? No, don't cry, Greg. I was like, no, not Beer's law. Yeah. Do you remember? Does anybody remember what Beer's law is? Anybody wants to be a brave soul? Nobody wants.
It's the absorptional light, right? It's like ELK or ELC or something like that, right? Epsilon, yeah, epsilon. Like epsilon,
It is an epsilon.
It isn't. Then it's like length and concentration, I think, or something like that.
Isn't that wonderful? I mean,
I'm scarred. That's why.
but you know, where is the
Those two beds.
remember this? That or this can be like that. Uh-huh.
Break me off though.
Huh?
Just ABC, where's D, E, and F?
Nothing. All right, this is your absorption. This is a constant absorptivity. This is distance. We'll talk about that when we get there, when you have a cuvette and you put it in the light. So this would be the distance that the light travels, and this is the concentration. So absorption is linearly related to concentration. And this applies only when we have monochromatic light. Beer's law applies only when we have monochromatic light. Meaning, what is monochromatic light? One wavelength. Or light within very, very narrow wavelength from each other. So at one wavelength, Beer's law applies. You would have a specific absorptivity at that wavelength, and then you will have this equation applies, and then absorption is linearly related to concentration. Okay, so why did I say all this? Because that brings me to diffraction. So what you see here is the incident beam lamp will have light with abundance of different wavelengths. Not one wavelength, polychromatic light, multiple wavelengths. So if I direct this light, all of it to the sample, and I want to quantitate, I won't be able to apply Beer's law. If you remember from caffeine, although you used a PDA where you got an entire spectra, you selected one wavelength, 272, to do quantification. So the incident beam goes into a diffracting or diffraction grating system or a prism to diffract the light, break it into individual wavelengths. So diffraction is really important when we want to select the wavelength for identification, for quantification, not for identification, for quantification to apply your favorite of all time, Beer's law. Okay, so that's diffraction, is very important. The other one that we use quite often in analysis is refraction. And we use it in refractive index determination of total solids, for example. So you measure the refractive index and you convert it to total solids. We use it in HPLC for carbohydrate determination. So what happens here is the light hits at a particular angle in, let's say, air, and when it goes into another medium, it refracts, and that refraction is proportional to the concentration of constituents within that medium. So that is important too. So now we have interference, diffraction, refraction. We explain it based on wave-like properties of light. But when we want to talk about absorption and emission, then it's better to explain it using the characteristics of pockets of energy or photon of light. Okay? And anybody would like me to repeat anything?
But I had like, so the reflection or the refractive, you guys like tell how much sugar with one water.
Total solid, if your solids are only sugars, then yes. Okay. So the wave is made up of pockets of energy, discrete pockets of energy, not a continuous scale, a discrete, and we'll talk about that in a little bit. We call them photons. These pockets of energy that travels, they call them photons. And this is the best way to explain absorption of light, by absorbing a photon of light and emitting photons of light. The energy of the photon is related to the frequency of the wave. So the higher the frequency, the higher the energy. So E equal H by frequency. The H is a constant. Okay, so we just talked about monochromatic light. So monochromatic light is a light with one wavelength or wavelength very, very close to each other in length. Okay, monochromator. Do you have that on your slide? Monochromatic light, electromagnetic radiation composed of waves having single frequency and wavelength. You can write it down. You have a question? Somebody have a question? I saw a hand, or I imagined a hand. Okay. All right. So monochromatic light is an electromagnetic radiation composed of waves that have a single frequency and wavelength. One wavelength, one frequency. Okay, so what about monochromators? Monochromators are the units that you have in a detector that converts polychromatic light to a singular monochromatic light. So in a detector, when you want to quantitate, you have a grating system where I don't have the thing anymore. Okay, so this is the beam of light. This is a mirror. So it hits a mirror that is angled in a particular way that the light is reflected onto a grating system. That grating system or a prism, so either a grating system or a prism, that will break the light into or diffract the light into multiple wavelengths. And then you have a slit, you have a plate with an opening that allows the specific lambda to of or wave of light with a specific wavelength to pass through to your sample from part. Or your flow cell where your sample is passing through like an HPLC in a tube versus the flow cell. So that slit, the system can be controlled and can be moved up, down, and then you can have different wavelengths reaching your sample. So you can, that's why we talked about variable wavelength detector, because we can move it. We can tell it to move up, down, and select for a particular wavelength to go through and go to your sample. Okay. Photon flux. So that means number of photons flowing across a unit area perpendicular to the beam. So this is a unit area. It could be the your covect in your spectrophotometer where you put the tube or the cuvette, and then is the number of photons, photon flux, hitting at the perpendicular angle to that surface area. Per unit time, and the intensity is that relationship. So intensity I is the energy directed at a particular area per unit time. So these are things we can control in a spectrophotometer. We can control the monochromator and select wavelength. We can control the intensity or the radiant intensity so that we increase sensitivity or reduce interference and the noise of the system. And we'll talk about that again later on. So these are things we can control in our spectrophotometer to either enhance sensitivity, to apply Beer's law, or to reduce interference. Okay. Again, here what I said earlier, the wavelengths, the smaller the wavelengths, you can see here the frequencies. The higher the frequency, the higher the energy. So you want to remember, energy is your constant times the frequency. And the frequency is the number of oscillations or repeated units per unit time. So the number of up and down oscillation per unit time is the frequency. And then your wavelength becomes smaller when you have high frequency. Okay, now, like I said earlier, the most important region is the ultraviolet, the visible, and the infrared. Ultraviolet above the violet, visible radiation, and the infrared below the red. And these are the areas where it's most relevant for food analysis or used in our spectrophotometers. So in this region, mostly the UV vis region is where we could have both absorption and emission. Sometimes only absorption is what we can measure. All the going from excited state to ground state can only be dissipation of heat for some molecules. But then in infrared radiation, it's usually absorption is what you measure. But sometimes we also measure light scattering, which that would be later on explained in IR. Okay, so what happens when an atom gets excited with the photon of light? So you have the valence electron. Do you remember those? So you have the valence electrons, and you also have the electrons in the outer shells that are in a bond, in a molecular bond. But if you have one atom, you have this valence electrons within this atom. When it's hit by a photon of light, if it is within its acceptable range of energy. I'm going to use this term, acceptable range of energy levels. Remember that, acceptable range of energy levels. So remember when I say it's not continuous, it's discrete levels of energy. And that's why I'm going to try to relate everything so that it makes sense to you. And I'm always going to use this simple example because you did it in lab. So you had here, you looked at your PDA, photodiode array detector. So you looked at a particular time, you looked at a figure, a graph that had nanometer, lambda, nanometer, and then you had absorption. And then for beam, you had, pretty much a hill, right? Was it, do you remember? And it was here you had your lambda max at 272 nanometers. You had maximum absorption. Let's say this is 310 nanometer. I'm going to take it all the way down so that. So this is 0. At 310 nanometer, you didn't have any absorption. It doesn't mean that this lambda doesn't carry energy. It's 310. It carries energy, but it wasn't an allowable energy level within that molecule. So it did not absorb it. So that's what I mean with acceptable energy level. So you have an acceptable range. If the energy that is hitting your molecule or your atom is within that allowable energy, it will absorb light. Otherwise, it won't absorb it. That has nothing to do with whether the energy is powerful enough or not. Okay, so let's say here your atom got hit with an allowable energy level. Then the photon of light is going to be absorbed by the electron or electrons in the outer shell, and they're going to move to a higher shell. And that is the excited state. So they go from one energy shell to the outer to another higher level, and they are in the excited state. They absorb the energy, but they don't stay there long. They want to go back. So when they go back, two things can happen. Either they just emit heat and go back to their original state, or they emit slightly heat and another photon of light. That is emission fluorescence. In this case, your atom fluoresced or your molecule fluoresced. What about the wavelength of the emitted photon? Is it higher or lower than the original one? Think about it. I said when it goes down from excited to ground state, there is some heat that gets dissipated, and then a photon of light gets emitted. Is the wavelength higher or lower than the one that hit the atom? Right. The energy is lower, and the wavelength would be higher or lower? Higher, longer, yes. So the energy of the photon emitted true will be lower, but lower energy, longer wavelength. So if you ever worked in a lab and you were measuring fluorescence, you would set your spectrophotometer to an absorbing wavelength and an emitting wavelength. And it's always the absorption wavelength is shorter than the emission wavelength when you're measuring emission. So you set your spectrophotometer to two wavelengths, the absorption one and the emission one. Okay. Okay. No, it's not very exciting to some of you. I don't know. I'm excited. It's excitation. It's going from ground level to excited.
Ground state, right? All right.
What can I do to get you to be with me on the excited level?
Shoot lighter. I'm not sure photons.
Ah. Oh well, Friday, right? Ready to go home?
No, gotta take out the dock this week.
Greta's leaving us. She's ready to go home.
Yes.
Okay, wait, come back to me. I have 10 minutes or so. All right. So you guys, atoms and molecules, are existing in the ground state today. Nothing I can do is going to get you to the excited state, but assuming we get to the excited state, so we go from the ground state to the excited state, the difference in the energy is equivalent to the frequency of that wavelength that got absorbed, or the photon of light that got absorbed. Okay. So the energy of the molecule or the atom increased by the same amount of energy that the photon was carrying. Okay. And this is what I was saying again earlier, that we have allowable levels of energy within an atom and within a molecule. Allowable energy for every atom and every molecule, and that's why the absorption spectrum is unique for every atom and every molecule, because every atom and every molecule have those specific energy pockets that are allowable. Okay, so we have three types of energy levels: electronic, and that has to do with the electrons that move into higher energy levels. So that's why it's called electronic. Vibrational for the bonds within a molecule, and rotational for rotation of the atom around the center of the molecule. So for the electronic are the ones that carry the highest energy or absorb the highest energy. The vibrational, they are smaller pockets of energy than the electronic, and the rotational are even, the levels are even smaller within that. Okay. And it will make sense to you in a minute, I hope. So the electronic energy has to do with the electron moving to the outer shell. Okay. So atoms and molecules can gain electronic energy. Both atoms and molecules, because atoms have the electrons, and within the molecules, you have atoms with electrons that are participating in molecular bonds. Okay, so this is relevant. The energy that is allowable under the electronic energy levels within an atom or within a molecule falls within the UV visible range of energy. So when you did, or you're doing the atomic absorption, we are detecting elements in the atomic form in the UV visible range. Also molecules like the caffeine, the energy that we are giving those molecules so that we detect them are within the UV range for caffeine. So electronic energy is within the range of UV vis. That's what I want you to remember. Now, vibrational energy, see, it's smaller. Vibrational energy packets are smaller than the electronic one. These fall in the IR range, infrared range. Infrared are longer wavelengths than UV and vis. So they carry less energy. So the vibrational energy is less than the electronic energy. So the vibration is within a molecule. Is there vibration energy in the atoms? Atom by itself? No. The vibration is within a molecule. The atoms are vibrating due to the bonds within a molecule. So there's no vibrational energy in atoms, but in a molecule, there is a vibration energy, electronic energy, and rotational energy. Okay? So the vibration is within the IR region. So these energy pockets fits within the IR radiation. So mid-IR, near-IR, lower energy than UV vis. Whereas rotational energy, like I said, within the molecule, the atoms rotate around the gravity of the center of gravity of the molecule. And it is smaller pockets than vibration and electronic. And it fits within the microwave range, but it's not relevant in food analysis. We don't use it for detection, identification, or quantification. But these are the three forms of energy. So again, like I said, the atom energy is only electronic. There is no vibration, no rotation. It's just the atom and the electrons of the outer shell. Whereas the molecule has all three forms of energy, the electronic, the vibrational, the rotational. This is a common question I ask. Maybe in exam, maybe in the final. What are the three forms of energy? There. Okay, so this is what I just drew here, is that the energy from a photon is transferred to the molecule. And not only that, there are allowable energy levels. That's why at different wavelengths, a molecule or an atom may or may not absorb light. And this allows us to get fingerprints for every molecule, because every molecule, if it absorbs light, it will absorb it differently, have different energy levels. This is the last slide, and I'll let you go. Emission of radiation, I already kind of talked to you about it already. For emission to happen, you have to absorb light first. And after reaching the excited state, dissipation of heat and some molecules or atoms fluoresce, gives out a photon. Only what you want you to remember: wider, longer wavelength, less energy, the photon that is emitted from the photon that is absorbed. Can I remember that? That's it, you guys. I can send you one. Just review the recap questions. We'll talk about them next week on Monday. Have a great weekend, you guys. And I'm gonna set you free 5 minutes early.
Now.
Do I get +2?